A 5 kilogram box slides down a 30-degree frictionless ramp starting from rest at a height of 4 meters. And we first want to use conservation of energy to calculate the speed of the box when it is halfway down the ramp. So, setting up conservation of energy. E initial equals E final, because energy is conserved. The initial part, we're referring to the top of the ramp, and the final part, we are referring to the halfway point down the ramp. So we're going to say Ki plus Ui equals Kf plus Uf, and the first thing you want to do is figure out which of those terms go to 0 to make our next equation simpler. So it says the box starts from rest, so the initial kinetic energy is 0. It is starting at a certain height, so it does have gravitational potential energy initially. At the bottom of the ramp, or halfway down the ramp, it is moving, so it has kinetic energy, and it hasn't reached the bottom, so it does have gravitational potential energy. So the initial kinetic is the only term that can be crossed off. So plugging in the formulas, we have mgh initial is equal to 1/2 mv squared final plus mgh final. Every term has an m in it, so we can cross off the m's. And then you're going to solve this equation for the VF. So I'll let you rearrange that to get the VF by itself. And you're going to plug in for the H initial, you're going to be plugging in the 4 meters from the top of the ramp. For the H final, that's halfway down the ramp, so the height will be 2 meters at that point. And if everything is done correctly, you should get a final speed, or a final speed of halfway down the ramp, of 2 root 10 meters per second. All right, in the second part, you want to use conservation of energy to calculate the speed of the box when it has reached the bottom of the ramp. So there's nothing really changed about this problem, except for the fact that the final location is different. It's now at the bottom of the ramp instead of halfway. So when you set up this problem, the E final, instead of representing the halfway point, would just represent the bottom point. So when you set up the Ki plus Ui equals Kf plus Uf. My style seems to be getting worse because I can't even read what that says. But anyway, the initial kinetic energy at the top of the ramp is still 0. And this time, since it's reached the bottom of the ramp, the final gravitational potential energy is 0. So the equation just simply becomes mgh initial is equal to 1/2 mv squared final. The m's cancel out. You can just solve for the VF again. So rearrange the equation and get the VF, and you should find that that is equal to 4 times the square root of 5 meters per second. In part B, now the ramp is not frictionless, so friction is a non-conservative force, which means that work is going to be done on the system, which will reduce the amount of energy we have. And the way you set up the equation this time, which we're going to do in the second thing of part B, is you do energy conservation by saying the initial energy plus the work done by any forces, any of those non-conservative forces, is equal to the final energy of the system, because the work done by friction is going to be negative, since friction points in the opposite direction of the displacement. So when you add a negative number onto the initial energy, it reduces that total energy of the system to a final amount, which is a little bit less than the initial amount. Now, energy is still conserved because this energy that was lost has just gone into increasing the thermal energy of the ramp, but this equation is just for the box sliding down the ramp and not including the thermal energy, since that was lost with this term. So in B part 1, we first have to figure out the work done by the frictional force on the box as it slides fully down the ramp. So I want to solve for this term right here, the work done by friction. And one thing to make sure you don't get confused on is this F subscript right here stands for final, as in the initial energy and the final energy, whereas this F subscript right here stands for friction. We're trying to find the work due to the frictional force. Later, we're going to see that all of the non-conservative forces, we just use W and C for non-conservative. So if you want to start getting in that habit right now, we can say the work due to non-conservative forces, in other words, the work due to friction, is equal to, and now this is where we just said earlier, the frictional force is pointing down the ramp, kind of going this direction. No, sorry, the box is moving down the ramp, going this way, but the frictional force is in the other direction, going up the ramp. The angle between something going down the ramp and something going up the ramp is 180. So we can use the shortcut formula, which is it's the negative force of friction times the displacement of the box. To get fully down the ramp, we know that the length of the ramp we solved for in a previous problem was 8 meters. So this D that we solved for back in the older problem is 8 meters long. We need to come up with what the frictional force is. And we do have an equation for frictional force, which is, because it's moving, mu k times Fn, and we'll keep that D on there. And that's equal to minus mu k, which is given. Now the normal force, if you remember what the free body diagram for this problem looked like, it had a gravitational force going straight down. It had the normal force going this way, and then we can add on a frictional force in this problem, since there's friction opposing the motion. When we break this gravitational force into components, we have an Fg sine theta directed down the ramp, and an Fg cosine theta that is perpendicular to the ramp, opposite of the normal force. So since the forces in this direction are balanced, because the block is not accelerating this way, it's only accelerating in this direction down the ramp, but since it's not accelerating this way, the forces are balanced. So using Newton's first law, this normal force is equal to this downward pointing force, this component of gravity. So Fn is equal to Fg cosine theta. So I'm going to replace this Fn with Fg cosine theta. And we can go ahead and plug in the formula for Fg, which is m times g. So we have mg cosine of theta, and then we still have that times d on the end of the equation. And now you know everything in this equation. We know the mu k was root 3 over 5. We know the mass of the box was 5 kilograms. The gravity is 10. The cosine of the angle, it was 30 degrees. So cosine of 30 is root 3 over 2 times the distance, which is 8. And all this stuff should simplify down pretty nicely to get a final answer of negative 120 joules. And again, it's negative because friction points in the opposite direction of the displacement of the box, so it should be negative, because when we add that negative number onto the initial energy, it's going to reduce it, so the final energy of the box is not as much. Since remember, some of that, well, all that energy that was lost due to friction went into making the ramp slightly warmer. That was converted into thermal energy. So let's go ahead and use this equation, and let's plug in the formulas. So we have the initial energy, Ki plus Ui, plus we now have that work due to non-conservative forces, is equal to Kf plus Uf. We're only concerned about the speed of the box right at the bottom of the ramp. So the initial kinetic energy is 0, since it starts from rest. The final potential energy, the gravitational potential energy, is 0, since it's at the bottom. So plugging in the formulas, we have mgh initial plus the work due to non-conservative forces is equal to 1/2 m v squared final. Can you cancel out the m's in this equation like we did up here? The answer is no, because This term, the WNC, does not have an m in it. We've already solved for it. I got negative 120. Now, if I had just taken this whole entire formula for WNC and plugged that whole formula in place of this, then I could cancel out the m's. But since I went ahead and solved for that, and that which already incorporates the m in it, I'm not going to be canceling out the m's. I'm just going to leave that as the negative 120. So rearrange the equation and calculate the speed of the box at the bottom of the ramp, and you should get a final speed of 4 √2 meters per second.